Pretty game changing. It says that a voltage is going to be produced by a changing flux. Again, magnetic flux is not going to create a voltage. A changing magnetic flux is going to create a voltage. This negative sign really just talks about the direction of the voltage, which is then the direction of the induced current. Okay, as a review, magnetic flux is the number of magnetic field lines that are penetrating through a surface. We typically get that, we say phi is equal to the accumulation of B dot dA. Again, it's just the number of field lines. If B is constant over the area, then the magnetic flux is typically just the B field times the cross-sectional area. If the B field has some sort of angle to it, then there's going to be a sine or a cosine. Just kind of depends on what angle is given. Okay, so if you think about different ways to change the flux, well, if the flux is BA cosine theta, then you can just change the strength of the B field, right? You can crank up the external field or decrease it. You could bring a magnet closer or move it further away. You could take the loop and move it closer or further away to a magnet, and again, you're going to change the strength of the B field, thus changing the flux. You can change the area of the loop that's inside the magnetic field, because really the flux, if you only have half of the loop inside a magnetic field and then you put the whole loop in the magnetic field, you're going to get more field lines, thus changing the flux, thus creating a voltage, thus inducing a current. Or you can even rotate a loop through the field. And it's kind of like, this is like, rain. So if the rain is falling down and you have your board or your loop totally like in line with the rain, then all the rain goes through it. If you tilt it, you don't get as much rain, and then if you put it all the way, right, you don't catch any of the field lines, you don't catch any rain. So rotating the loop would also change the number of field lines, which is changing the flux. Okay, other guy who gets some credit in here is we have Faraday's law, which says that the induced voltage, and really there's a capital N in here because if there's more than one loop, then it's going to induce more a bigger voltage. And then Lenz's law really deals with the minus sign. It says that the induced current will flow in a direction that opposes the change in flux. Again, the negative sign is kind of like the negative sign in Hooke's law of F equals negative kx, where the force of a spring is in the opposite direction of the displacement. Here, the negative sign tells you the direction of the induced current, and it will always oppose the change. And again, we'll go through examples of that. Again, it's all about the change. So Faraday tells you the voltage produced by a changing flux. Lenz tells you the direction of the current that will oppose that change. I'm going to take you through 3 examples of this. So first example. So we have this external magnetic field. Don't worry how that's created. It's just there, and it's X's. So the magnetic field is into the page. And then we have this red wire, which is our loop, and it's just a rectangle. Do you see how the B field is a function of time? So the B field is changing. The B is actually constant over the area. So the B field in this part of the loop, and this part of the loop, and this part of the loop isn't changing. So the flux is just BA. Faraday says that the voltage produced is the time derivative of the flux. The flux is just BA. A is a constant, but dB dt is not. dB dt, if we take the derivative of this guy, we just get 5. And we say then that the voltage produced would be 60 volts. Now, the current is going to oppose the change. So let's look up here. See how I have X's? Right? The initial B field is a negative 10, which is into the page. But I'm increasing the B field, making it less negative. So I'm getting less X's. And the current and the loop is like, no. I want all the X's. If you're taking away X's, I am going to induce a current, the green, in this loop to create more X's. So take your thumb and put it on the bottom, and then the wrap rule would say that if the current was going to the left on the bottom, that would create, by Ampere's law, more X's. Again, the current's direction is always going to oppose the change. So if your B field has X's and you're losing X's, the induced current will produce X's. It wants to maintain equilibrium. It's always going to oppose the change. So the induced current would be clockwise in this case. Again, the induced current is clockwise. You're actually increasing the B field, and the current will oppose the change and create its own field to oppose the decrease of X's. And again, if you actually knew the wire's resistance was 20, you could figure out that the induced current would be 3 amps. And as long as the B field is increasing at this rate, you're going to continue to induce a current in the loop because it's always going to oppose the change. Again, you're getting less X's, so the induced current has to create X's, and a clockwise current in the red loop will actually create X's inside a loop. Again, you don't care anything about outside a loop. You're talking about the fluxes inside the loop. Okay, that's my first example. Example 2, currently, here's a loop, and it has no flux. See how there are no field lines going through that loop? And what you're going to do at first, you're going to move the loop into the field, whoom, and you're going to give it flux. Thus, a rate of change of the flux will then produce a voltage, which will produce a current. Okay, so go with Faraday. Faraday says that the voltage is the rate of change of flux. Flux is B times A. Now, in this case, the B field is not changing. The B field is a total constant. But the area of the loop in the flux is changing. The area is just length times width. Now, if you think about it, this length here is not changing. It's this amount of the loop, this little width here, that's changing. Well, how fast is that changing? What's the time derivative of d? Well, that's what we call velocity. So it turns out then that the time derivative of flux, which is B times A, B is a constant, L is a constant, and so the only thing we actually take the derivative of, we take the derivative of the width. And the time derivative of the width of the loop in the field is actually V. So then the voltage is negative BLV. Since we know V equals IR, BLV is the voltage, divide by R, and we get the current. Okay? The current, again, what direction is it? Okay, so in this case, the original loop didn't have anything, no dots. You throw it into this field and you give it dots. It doesn't want dots. So then the induced current will try to create X's to cancel the dots you're giving it. Again, it doesn't have any flux. You're giving it dots, so if you go around this loop clockwise, left on the bottom, using the wrap rule, that will create X's, and the X's will attempt to cancel and oppose the dots. Okay? Also, we know that, again, I'm going to say the word oppose about 1,000 times. We also know that this magnetic field will oppose this guy from even entering it. So if we think about what direction should the current be right there such that the field rejects the loop? Well, now we're going to point our thumb down, our fingers out of the page, and then you can see that the palm goes left. The field is going to reject this loop. And that's another way to indicate that the current in the loop is going to end up going clockwise around. Okay, and again, it's going to oppose it. If you wanted to know the force on this thing, well, F equals ILB, and then we could put this in for I, and we could actually then find that the force on this loop is a certain value. Oh, looks like I did it down here, right? F equals ILB. We know that it's going to reject the loop. There's the current induced, and then this guy is then the force on that loop. There's no force over here because it's not in the B field. There are forces on the top and the bottom, but they actually cancel. The force on the bottom is up, and the force on the top part of the loop would be down, and those cancel because that's how vectors work. Okay, the loop is moving. Okay, so the loop is entering, and now let's say the loop is actually inside this thing. As the loop moves inside, what happens? Nothing, because there's no change in flux. As you move this rectangle and it's all in the magnetic field, it's the same area and it's the same B field, so it's the same flux. Thus, nothing happens when you're moving inside of the thing. Okay? No change in flux, no voltage, no current, no force. Now, the third part of this scenario is that you're going to take the loop now, and it's going to look like this, and you're going to pull it outside. And it's like, oh man, I have all these dots, and now you're trying to take the dots away. So what has to happen? An induced current will try to get back dots. And so the induced current now is going to flow this way. It's going to flow counterclockwise to produce dots to try to get back the dots that it already had. And that's what I talk about down here. It's the same analysis, except current will flow counterclockwise. The force will be left because it's going to oppose it trying to pull out. Like, you're going to have to force it out because it doesn't want to leave the field. It's always going to oppose the change. Okay, and this last example is the hardest example because it requires a decent amount of calculus. All right, so we have to be careful. If I'm talking about the current in the wire, I'm talking about this current, which is a function of time. If I'm talking about the induced current, meaning the current in the loop, well, I will have to say the induced current. Current in the wire, induced current. Okay, so look what happens here. I have this wire, infinitely long wire running here, and the current is some function of time, 4e to the negative 2t. Think about what's happening over time. This current up here, in this space above it, is dots. Below would be x's. We don't care about below because our loop is above. So we have dots in the loop above, and this is a negative exponential, so you are losing dots over time. So then your induced current in the loop, this current, has to move to the right, meaning counterclockwise, because that will produce dots. You're losing dots. The induced current will be in a direction such that it opposes the change. It will try to replace whatever happened. Again, that's what lenses says. Okay, the hard part here, and in this particular case, that the flux isn't just B times A, because the B field's not constant over this loop, because we know that the B field created by the current in the wire is mu naught I over 2 pi r based on Ampere's law. Okay, so we have to break this loop into strips. The reason we break this thing into strips is because each strip has a constant B field. And so the area of each strip is the length of the strip, d, times the little bitty thickness of it, dr. So this is our dA, and so this is how we have to find the flux. We have to accumulate the B field over that two-dimensional area. So we know the strength of the B field is mu naught I over 2 pi r from Ampere's law. We know dA, the area of each strip, is just capital D times dr. We do that integral, we get a logarithm, and then we do get the logarithm of a plus L minus the natural log of a, which we know that the subtraction of logarithms is the division of the argument. Okay, so this is the flux going through our loop. Now we got to think, okay, how is that flux changing? Well, it's changing because this silly current is decreasing, which causes a decreasing B field, which causes a decreasing flux. So we need to take the time derivative of this flux. The nice part is the only thing that's a function of time here is the current. So everything can get factored out. This is all just a constant. And then we take the derivative of I. The derivative of E, oh man, that's stupid. That's a negative sign right there, and I forgot that. Right? That's a negative sign. That's a negative sign. I just dropped it. Silly, right? It's right there. So the derivative of this current, the derivative of 4e to the u is 4e to the u times u prime. So I'm going to get that negative 8 e to the negative 2t. So there's a negative there and a negative there. Okay, so then this then is the voltage produced because that is the rate of change of flux. Well, if you want the actually induced current, well, then you just take the voltage and divide by the resistance. The direction of the induced current is counterclockwise. It's counterclockwise because a counterclockwise induced current produces dots because you want to oppose the change of this B field decreasing because of a decreasing current. Okay? Those are the three most popular examples of how you can change the flux in a loop, thus induce a voltage, thus induce a current. The magnitude of the current is really based on Faraday's law. The direction of the current, we give credit to Lentz. Lentz says that the induced current in the loop will always oppose the change. Okay? Again, these notes are on Canvas. Feel free to download them, watch this video, and go through. But a lot of the AP free response questions that you're going to do, like 9 or 10 of them, some of them are very, very similar to these 3 examples.